Hello everyone and welcome to the last session of this wireless masterclass provided by Shure with best practice and techniques for your RF needs. A little bit of housekeeping as an introduction. You have a chat window where you can interact between yourselves and us. And you also have a Q&A section dedicated at the right of your screen. Please, if you want to share any question, do it there. On top of that, my colleague Marwan will propose some polls that are some questions here and there, just to keep you busy and to understand if I'm explaining things right or not. So we have been looking to several topics from RF fundamentals, analog and digital RF, in-ear monitors, the basic of frequency coordination, and today as a last topic, last but not least at all, we have antenna placement, cabling, antenna distribution for large systems. They are three topics, but they end up being one. This is why we decided to put together. After that, or maybe after the session, we will have a short discussion about Shure Audio Institute offering, because the wireless masterclass is definitely not everything we offer. We have targeted wireless workbench training and also an RF coordination workshop that we cannot see the time to be able to deliver in person, because this thing cannot be done online. So it has to be in person. And we are hoping end of 2020, early 2021, as soon as the conditions will allow it, to be able to deliver it again. So, what's the topic of today? The first one is the antennas. Antennas are transducers, just as a microphone or speaker. They transform one type of energy into another, and as you can see in this amazing animation, they are always polarized. We spoke about polarization between electric and magnetic field in the beginning. I hope you remember it. And the polarization is something that we need to remember when we go to place our antenna. Most of the antennas can both transmit and receive, but not all of them. And we will see more in details how and why. So here we have some, I'd say, most of the antenna types that Shure is offering, and let's see how they are categorized. First of all, the size of the antenna that has to be proportional to the wavelength. Maybe some of you already heard about quarter wavelength, half wavelength. Let's say that for professional users, we do not really consider a quarter wavelength antenna as an option. We use a half wavelength antenna. Why half and not full wavelength? We can say that the half wavelength antenna offers the best efficiency, related also to the dimension of the antenna itself. The second criteria to define antennas is the pickup pattern, or in case it's used for transmission, the transmission pattern. They can be related to microphones, so we may have omnidirectional antenna, cardioid, supercardioid, shotgun antennas, half cardioid, but they are not always exactly as the microphone. So one omnidirectional antenna is not behaving exactly like an omnidirectional. We have wideband and narrowband option, so they can operate into a wideband, or they are focused on certain frequencies. And then there are two other criteria that are related to the gain. One is the amount of forward gain they can offer, and the second one is the active electric amplification that they can have. So The antenna dimension is the first criteria that we look into. So if we consider that UHF frequency length is wavelength is about 50-60 centimeters, we expect enough wavelength antenna to be around 25-30 centimeters. While for a VHF, that is a much bigger wavelength, we have bigger antennas, as you can see in the drawing. Usually we operate with dipole antennas. Can be more complicated or less complicated, but they all have a sensitivity divided, as you can see. So towards the center of a dipole, there is more sensitivity than towards the extreme of a dipole. Therefore, an omnidirectional antenna is not purely omnidirectional, but if we look at it in a 3D, with a 3D graphic, it will look a little like a donut. So not much sensitivity at the bottom and top of the antenna, and the maximum sensitivity on the long side of the antenna. I said quarter wavelength antenna are not very relevant for us, so I'll talk about them now and not anymore. They cannot be remoted. They usually need the chassis of the device of a receiver to act as a ground plane, to kind of reflect reflect some waves and use their reflections as a virtual dipole. So they are not really interesting for us as a professional users, and they are common in entry-level consumer-oriented products, but not for pros. As I said, we have omnidirectional antennas. Shure, most of the Shure devices are coming with a UA8, that is an omnidirectional narrowband antenna. But sometimes you may need the big one, the second one in the picture, that is the UA860. Why you want it? They have exactly the same polar pattern. They have exactly the same forward gain that is considered to be a couple of dBs, 2 dB, compared to a non-existing ideal fully omnidirectional antenna. The difference is that the UA8, the small one on the left, is narrow band, while the UA860 is wide band. So it can accommodate frequency between 470 and 860 megahertz. But other than that, they behave exactly in the same way. Now here we have a directional antenna. That's specifically the UA874, but the concept is not different for other brands and other models. So shark fin antennas. I invite you not to consider the small amplifier sitting on the back of the antenna, but just thinking about the antenna. It has a forward gain related to the design itself of something between 5 and 7 dB. The pickup angle is about 120 degrees, so we can think of it as a cardioid antenna. Of course, it's polarized, so it makes a difference in measurement if it's in a vertical stage or in a horizontal stage. When we think about directional antennas, we should not only think about, okay, I can pick up more of my mics in that direction, but also that there is an area where they are less sensitive. And this can help us to reject some unwanted signal. The same thing is applicable, honestly, to narrowband antennas. Of course, ideally, a wideband antenna can catch everything. That's good. But can catch everything and can also catch things that are out of our bands. We spoke in the last session about walkie-talkies, an example. They are an issue. They can be a concern for us. So the narrowband antenna have their own value. Sometimes you may want to use filters coupled with antennas just to prevent unwanted signal to enter your signal path. This is the half cardioid antenna. This is typically for installation. It looks like a Wi-Fi router. So It's very easy to hide in certain installations. I don't see it much in use in temporary installation, rental companies. It's more for fixed installation, and its pickup pattern is half cardioid, I would say. So a little more narrow than the one we saw before, but it has to be mounted on a hard surface like a wall or the ceiling itself, and it can cover about 100 degrees. The forward gain in this case is between 3 and 5 dBs. Last but not least, the helical antennas. I said almost every antenna has a polarization, and even these antennas have a polarization, but this type of polarization is circular. So if we turn the antennas that is acting as a source, let's say by 90 degrees, it will always show the same result at the output of this antenna. So they are in use for systems that are seeing a single antenna for transmission, specifically in-ear monitors, but they are used with some success for microphones as well. The forward gain of this antenna, that I repeat, forward gain has nothing to do with the amplifier itself. The forward gain is about 10-11 dB. Now I invite you to remember these three numbers: 2 dB for omnidirectional, 5 to 7 for shark fin antennas, and 9 to 12 for helical antennas. And keep them on the side in your mind, because we'll use these numbers very shortly. As I said, we mostly have wideband antennas into our portfolio, but we also offer a lot of narrowband antennas. Usually when you buy an Axiom Digital or a PSM 900, it comes with its own narrowband antenna. They can operate on a span of 150 megahertz, but usually they are tuned for optimal performances for about 60 megs only. And here is a little memorandum for your forward gain. But again, it's related to the design of the antenna itself, because if we are dealing with an active antenna, that's another step of gain. So the onboard amplifier helps us to compensate for signal loss happening because of cabling. So the only reason to use this stage of gain, is that our forward gain is not enough to compensate the loss that cables are introducing. There is no other reason to use this gain staging, and it's not helpful for us if we use it differently. Why it's not helpful, more gain? Because in the moment that we raise up the signal, we raise up in the same way the noise floor. And as we said before, RF transmission is all about signal to noise ratio. So if to increase our signal, we need to increase our noise, we don't get any benefit. So the only reason to use this electronic gain stage is to compensate cable loss. How do I choose my antennas? Generally, I choose an omnidirectional when I need to cover, I wouldn't say largest coverage area. Mostly it's when I'm in the center of something. Let's say that I have the opportunity to place my antennas somehow in the center of my stage. I don't actually need to cover too much. So the space I need to cover is about 30 meters or so. Omnidirectional antennas are working fine. I use directional antennas when I need to cover something that may even be smaller but more targeted. So I want to reject something that is not what I need, or I need to cover long distances. When I need to cover long distances, then directional antennas can be really helpful. The In this case, the gain we are taking advantage of is the forward gain that comes with the device itself, with the design of a device. And what active antennas are for? To compensate for long cable runs. I think I repeated this 3 times only today. Most likely I will do it many more times before the end of the day, because one of the most common misunderstanding in RF, one of the most common mistakes I can see around is the excess of gain. When our system is too much sensitive, all we end up having is distortion. Imagine the input stage of the gain of your mixer. If you push it too hard, what you get is not a better signal, it's just distortion. Same here. In RF, we need to have a right amount of gain, not too much. And usually I see that there is too much gain in our chains than the opposite. After we decided what antenna we want to place, then we need to place them. And this is another area where I see urban legend populating the industry. And I've been myself a victim and as well teller of urban legends. So I hope in the old times. So I hope now that my mind is a little more clear, I can help you demystifying antenna placement. Let's start from the simplest thing. I have 2 antennas connected directly to my receiver. How I want to use my omnidirectional antennas? Open by 90 degrees. And this is valid not only for my omnidirectional antennas, this is valid as well when I have shark fin antennas. Why I want them to be in this way? Because one antenna or the other one will fall close to the polarity of a transmitter that can change. Bear in mind that most of the time we lose more energy because of polarity mismatching than because of distance. So it's easy to lose if we go, like say, from 15 to 25 to 30 meters, we may lose only 3 to 6 dB. But if we change the polarity of the transmitting antenna by 90 degrees and both our antennas are standing straight, sorry, we may lose 9 to 12 dB, maybe sometimes even more. Sorry, I was drinking a little water. When reflections come into place, the loss can go up to 16, 18 dBs. This is why we should always keep our antennas a little bit open. Sometimes on stage or during installation, it's not always possible to have a 90 degrees angle for aesthetical reasons because they use too much space and whatnot. But we should always try to keep this phase, this polarity separation as much as we can. Except for the antennas that have to be mounted on the wall, we should try to avoid parallel surfaces. Especially, we should try to avoid to stick an antenna very close to the wall. Reason being, we create interferences that are in reflections that are really short between the antenna itself and the wall, and this can really degrade our signal by several dB. Of course, if the wall is a metal surface, it's clearly even worse. Or if it's a truss, again, a metal surface, this is even worse because the wall itself or the truss itself will be acting as an additional antenna, taking energy away from where we want our energy to be. Transmitter to receiver spacing. The minimum is, of course, I mean, we can go closer for a few minutes, but generally we don't want our receiving antenna be closer than 3 meters from the transmitter. Why so? Because we don't want to distort our input stage. So a powerful signal very close to a receiving antenna may increase the chances to have a distortion. So 3 meters as a minimum distance is okay to be calculated. And Of course, there may be exceptions, but I'd say not really below 3 meters. So sometimes we want to keep our antennas closer to the receiver. In case we have a U874, we may even use a -6 dB pad to prevent the distortion at the antenna stage and to make the antenna virtually a little more far from the source. But ideally, do not go below 3 meters, obviously, when the mic is operating. When you take it back, if you are the monitor engineer and you take back your microphone and then it's very close to your antenna, that shouldn't be a concern. Then there is another big territory dominated by urban legend. The distance between the two diversity antennas. I think it happened to any of us to enter a theater and see antenna A on stage left and antenna B on stage right. Okay, this is the only thing I call a mistake, a bad practice. Other than that, as long as the two antennas are in a reasonable distance, I never experienced specific issues or problems. If you speak with the best free RF coordinators you know around, none of them will probably give you a specific number like, oh, one wavelength is perfect, or quarter wavelength, or two wavelengths, or whatever. Generally, we can adapt ourselves to the show we are serving. So if we need, for any reason, to keep the antennas a little more far is fine, a little more closer. As long as they are not one on top of the other, it's okay. For installations where you have a monitor console, usually the dimension of a monitor console is the perfect distance between the two antennas. So you keep one antenna to the left of the mixer, the other antennas on the right of the mixer, and you are perfect. If you have, I don't know, a piece of truss next to the left side of your mixer, you just move the antenna 1 meter away and it will work. So there is not such a thing like a magic distance that will help you having perfect results. It's just a matter of common sense. Do not split them too much apart because over 3 to 5 meters, then diversity system struggle more when it's time to move from one antenna to another one. Or, in case of Shure, to combine the two antennas. Other than that, sometimes we may have in-ear monitor, transmitter, and two receiving antennas for mics. In this case, we selected the HA889 and two U874. The ideal distance between these antennas is about 2 meters. And this is the minimum. Do not go closer than that. This is a recommendation. Why is this a recommendation? Because we know that the transmitting antenna that can shoot 50 or plus milliwatts too close to a receiving antenna may create troubles. As simple as that. So a couple of meters between your in-ear monitors and your microphone antenna. Another trick is trying to avoid to have them on the same line, but use a little bit of directivity to reduce as much as possible the leakage. If you have a setup like that, you can try to align the three antennas and then move a central one. Maybe you shoot as much power as you can in the in-ear monitors, and you see where you get the overload in the receiving antenna. That's the wrong point, and you should do something different. Usually, the area where it's more easy to get an overload is when the three antennas are on the line. If you can put the in-ear monitor a little more in front or a little more in the back, it will benefit of a directivity of a transmitting antenna or a receiving antenna. Of course, some recommendation. Human bodies can be a concern because human bodies are made of water. Water is absorbing a lot of radio frequencies. So we should try to place our antennas as above obstacles as we can. The attenuation of a body can be really significant. So if you look at the graphic, we may easily lose 15 to 20 dB because of our mass or the talent's mass. And if someone is clearly much bigger, this can even be a bigger problem. So whenever we use simultaneously maybe a large amount of body packs, when we are placing our antennas, we should consider body absorption as well and try to minimize it as much as possible. Now, I will never get tired saying that a dropout doesn't happen because one thing goes wrong. It's not a deterministic um, technique that will save our life. We should just try to reduce as much as possible the chances, the probabilities of a dropout. There is not such a thing like a perfect installation, or there is not such a thing as a single small thing that will create a dropout. The dropout happens when 2, 3, 4 things go wrong. But as we cannot predict the behaviors, we cannot always predict which polarization the body pack antenna will have, because maybe it's just got a little bended or turned upside down or whatever. We should just try to reduce the probabilities of something to go wrong. Antenna symmetry is not mandatory. So there is no such a thing like, oh, you need to use exactly 2 identical antenna. You can have 2 different cable lengths if need be. In this case, it's highly recommended to compensate with the amplifier at the antenna stage, or with an amplifier, with an independent amplifier like the Shure UA830, to compensate the cable difference. But if one cable is 5 meters and then the second one is 7.5, your system is not going to suffer, and that's going to be okay. When we talk about cables, we will understand exactly what are the numbers that can affect and what are the numbers that cannot affect our system. We can use different types of antenna, yes, but we shall remember in any case that it's not that one antenna can cover one area and the other antenna can cover a different area. They have to get along. There are specific antennas like the diversity fin made by RF that are one directional and one omnidirectional with different polarization. So this proves that we can use different antenna types. But the idea is that we use different antenna types because we need, or because we solve a specific problem. But generally, despite what's written on your screen, I still recommend to stick to a symmetric antenna setup. Will put less stress at the receiver. Now, this is a small activity that I will run by myself. Luckily, we are not sharing, we are not all in the same room. So I will show you some mistakes in antenna placement. And I start from this one, and I start saying that actually the guy who built this rack had a very smart idea, because he placed the antenna 90 degrees apart, high enough to go over the head of the people sitting in front of him. The mistake here is that he had to install his front of house in a cage. This is not uncommon in America. I guess I never, ever saw anything like that in UAE or in Middle East. Maybe a place in South Africa had something like that. So the idea was brilliant, but unluckily he had to install his rack inside this cage, and because the dimension of the holes compared to the wavelength is too small, this cage is perceived as an obstacle by our radio frequency. This is the baseball field. Actually, they are multiple baseball field. You can see that the little kid is singing, and the receiver is placed behind the metal fences again. And again, the opening in the metal fences are too small to let RF waves to pass, so they are creating problems. We wouldn't have a problem with the receiver directly next to the camera or just in front of the metal fence. This is another mistake, not so common, but I have an emotional bond with this thing, because this is the first picture that I received immediately after I joined Shure. When I started at Shure 5 years ago, I was an application engineer, and this is the first request for help. It took me a bit of emails before understanding that these two antennas were installed inside a metal rack. So antennas in a rack are definitely not a good option because we need line of sight. Here we can see multiple mistakes. Okay, first of all, you may notice that there is a microphone that is not Shure, and this is a very bad behavior, but I really do not you, but I'm joking, obviously. We have the problem here is that we have too many antennas too close to each other, and they are not helping each other. Plus, there is a second mistake. We have 4 antennas plus 4 antennas, but the Revolabs are on a different frequency band, so let's ignore Revolabs for a moment. We have our two ULXP at the bottom of the picture, and we have 4 antennas on top of a rack. That's fine. The problem, as we saw last time, is that inside that box, especially with a very old product like ULXP, we may have intermod created by the two different receivers. So in this case, 2 antennas only and a small antenna signal splitter would have been extremely beneficial. Oh, here, someone wanted to hide the antennas. That's a good thing. Don't overdo it. In this case, having an antenna behind a false ceiling, it's not suggested. Now, if a false ceiling is just fabric, that may be the antenna work, but generally, free line of sight is highly recommended, and it's not recommended to keep the antenna so close to piping and structural cabling and other things that may really affect the efficiency of our antenna. Another recommendation is use the antenna combiner or splitters whenever you need, but don't use more than one. Here you can see there are two Shure UA2221, and at the output of each of them, there is an additional T-splitter. Don't do it. The reason is that at any split, as it's happening for any combining action, you lose 3 dB. Losing 6 dB in splitting, it's a bit too much. So out of your small energy, usually you don't reach your receiving antenna with more than 0 point something milliwatt. Losing 6 dB means that you are losing a lot of the 0.7 you have, and then you may find yourself at the output of a cable entering the receiver, very different receivers with not enough strength. A little checklist on best practices. Place your antennas as high as you can, above audience or other source of obstruction. Place as close to the transmitters as possible, just not too close, to prevent the overload of a receiver's front end. Try to keep them away from other sources of interferences, and this is including, as we saw, LED screens, as much as it can include the antenna of in-ear monitors, and use the benefits that directivity can give you in order to prevent bad signals to enter your path, as much as in order to prevent your signals to go on your way when you don't want them to. RF cables is another hot topic. Cables are as important as antennas, as important as microphones, as important as every other piece in our journey. Now I know it's a bit strange to talk about cables when we talk about wireless, but we all know that we need to connect usually the antennas to the rack units or to other units like antenna distribution and combiners and whatnot. So yeah, even if it's wireless, we need some cables here and there. So let's try to use the right cable. Just 1 second, a sip of water. Now we standardized and we use 50 ohm cables, coaxial, all of them. This should be very clear. We use 50 ohm cables and 50 ohm connectors. 75 ohm cables and 75 ohm connectors are for other purposes. Can be a MIDI signal, can be a video signal, but not for a ref. Now, many times I received this question, but can I use, does it work? Yes, a 75 ohm cable most of the time somehow works. But as we said, that the dropout is the consequence of multiple mistakes. This is a big one to start with. So I highly do not recommend to use 75 ohm cables in any case, especially not for long range, but not even for very short range, because the loss is very significant, and we create also standing waves inside the cable itself with significant cancellation. And even if we use the perfect cable, 50 ohm cable and connector, we have a loss happening. Overall, we can accept around 5 dB, 6 dBs of loss through the cable, but more than that, we are using the wrong cable. So how much energy a cable is losing, this is depending on frequency. So you can see that the loss at 200 megahertz or 600 megahertz is different, and length of a cable itself. Now here, this can be a little confusing because here we have 3 types of cables and the relative loss that is related to the length of a cable. So as you can see, for very short connections between 0.6 and meter and 3 meters, we can use RG58. Why we use RG58 at Shure? Because first of all, okay, it's not very expensive, but it's a little thinner and very flexible. So why not use it as long as the cable loss is not relevant, and 1 dB is totally acceptable. But when the cable gets longer, we cannot have RG58. So we decided to select RG8XU. This cable is performing better. It's slightly more thick and a little more expensive, but still, I would say it's a mid-tier cable. We use it up to 50 feet or 15 meters because the loss of a 15-meter cable of this type is about 4 to 5 dBs. So still in the acceptable range. For longer cables, so 30 meters, we selected the RG213. Why we didn't select the RG213 for shorter cables? If you ask this question, is probably because you never tried to put it in a fly case after a show. RG213 is somewhere in between a cable and a water pipe. It's very thick, it's very hard to bend, you cannot do sharp corners at all, it's a bit heavy, it's also expensive. So we realized with RG213 only the 100 feet or 30 meter cable that has a loss of 6.2 dB. Other than that, so we don't have longer cables because we do not recommend to use longer cables that are longer than 30 meters. If you need to cover, let's say, 50 meters, you can use 213 in a row, but having an amplifier in between. It's not recommended to use cables that are longer than 60 meters, no matter how much amplifiers you put in between. Never ever use more than one amplifier stage, and I do not recommend to go over 60 dBs. 60 meters, sorry. As you can see, in 2.4 gigahertz, we have to use different cables. The RG8 is having different performances, but generally we don't really work much in 2.4 gigahertz, so we can skip it. Here you can see that the different cables are having different performances, and if you see a 30-meter length as a standard, you can compare the different type of cables, and you can understand how frequency is affecting the cable loss as much as how the cable itself. So for the same length, with RG58 we may lose up to 15 dB, while RG8XU is losing only 8, but RG8XU is losing only 8, but RG8U or RG213 are losing below 6. There are other cables that are a little bit considered boutique cables. They get really expensive, up to $6-9 per meter. That can be used for fixed installation, but they are really uncomfortable and it's really difficult to bend them. They are very thick. So if you have long cables, you can use an antenna amplifier as displayed here. Be careful not to overload the input of a stage and not to exceed with the gain introduced by the amplifier. Another couple of accessories that is good to know are there and can get handy. They should definitely be in your emergency suitcase, are the BNC inline power supply. So imagine you have a QLXD that is not providing the bias power, or you have a passive splitter that can send energy only on one of the two sides. In that case, you need to add power to your BNC line, and this is why we introduced an accessory like the BNC inline power supply. You connect it to the power and you add the bias power to your RF line. Very important, we always need to make some calculation. And this calculation, there is a wizard online for Shure devices to make it, but we can do it also on our own. It's not a calculation that requires a software. We have the forward gain of the antenna as the first information. So you remember the 2 dBs of an omnidirectional, or the 7 dB of a U874, or the 11 dB of a HA889. This is our first information, antenna gain, plus amplifier gain if needed, minus cable loss, and we always have it. This is why it's important to know which type of cable we are using, because in this, and how long it is, because so we can calculate using this simple tab and calculate how much loss our cable is introducing, minus split loss. In case we have passive splitter, we may calculate a 3 dB per split, and the overall result has to be plus minus 3. Ideally, should be in that range. So the amplifier gain has to be used only if our result, without introducing any gain from the amplifier, is -4, -5, or even -6. -3, 4 dB, it's still very much acceptable in our setup. As I said, we shouldn't go with cable over 60 meters. But what if, for some reason, we need to go on top of a stadium cover, of a stadium roof, or we need to cover distances that may be 100, 150 meters. In this case, we have a solution. Actually, I'm not meaning Shure in this case. but there is a solution that is RF over fiber. Now, I did some installations, and I always prefer to rely on the Wisicom, that is probably a little bit like the Rode and Schwarz when we talk about analyzers. A great tool, amazingly expensive, but really, really powerful. There are alternatives to Wisicom, such as the Violite, RF Venue as another solution. I chose to display Wisicom because it has the full control. So it has filtering, it has gain control on dB, on input and output at steps of 1 dB. So it's very precise, very powerful. Why do we need such a powerful machine to convert a RF over fiber? Because the fiber itself has a very limited dynamic range. Out of about 100 dB that we can have of dynamic range in one antenna, 50% of it, so 50 dB, are gone because of a fiber. The noise floor inside the fiber cable is about minus 50 dBm. So RF over fiber is cool if you really, really, really need to use it. It requires a lot of planning. It requires, most of the time, it requires external filters, and it's definitely not a plug and play solution. So I heard sometimes, okay, but why you don't do antenna over fiber? Mostly because you are introducing a bottleneck that you don't really want to do. So whenever you're asked to cover long distances, try to avoid it. Then you try again to avoid it. Then you strongly try to avoid it. And if you really, really, really need to cover 190 meters, 100 meters plus, you can rely on fiber. But in that case, save yourself a day or two just to set up the perfect gain on your fiber to make sure that your operational range doesn't get too much affected by the fiber itself. Did I discourage you enough to use fiber, or can I do it more? No, fiber is great, but can be really complicated. Last topic of our wireless masterclass is antenna distribution and large. Now here, I'm not expecting to cover all the possible things related to antenna distribution or forget about large installations. I just want to highlight some points and show you a couple of examples that can let you understand how things can get done. So let's start with some important considerations. One of them is, are you using more than 3 systems? Then you definitely need antenna distribution system. Are there hidden remote receivers? Then you definitely need, if we are talking about receivers, remote antennas and antenna distribution system. If you require long range operation, you definitely need remote antennas, and most likely, if it's more than 1 or 2 channels, antenna distribution system. Without going too much in details in regards of a different antenna distribution systems in the market, even Shure has 3 options. I just want to have you understanding the purpose of it. So first of all, you do not build forest of antennas, you streamline, you have 2 antennas only that can serve as many receivers as needed. So you prevent closely spaced antennas for the receiver, you prevent the intermodulation happening between the different receivers, or you minimize it, and you can use one set of antennas for all your receivers. Okay, let's skip this topic without going too much in details of the science behind antenna distribution and splitters. It's not really helpful for us as users. What we want to know is that any passive split, like every time one signal is divided in 2 we lose 3 dB. While with active splitters, that means after 50% of the power, so a lot of it. So if we have, let's say, 0.8 milliwatts, after a split, we will have 0.5 milliwatts. But 0.8 milliwatts reaching a receiving antenna is a lot. Most of the times, our value will be lower. So once we split it, we may not be sure to have enough signal to feed the receiver. Active splitters can feed with one pair of antenna 4 to 5 receivers without loss. So if we have, let's say, a minimal system, 2 receivers only, we can rely on passive distribution, on passive splitters. We use a kit, a UA221 kit, 1 input, 2 outputs, straightforward, we are happy. Of course, we will distribute the cable, we will do the cabling correctly, but as soon as we have more than one couple of two receivers, then we need to rely on antenna distribution systems. These are 2 examples. They can feed 4 or 5 receivers each. They can be cascaded as well. So this is active distribution at one level. We have one distributor feeding 4 different receivers. Here, we use the cascade port, and we can feed up to 8 receivers. Now, we are already having a significant amount of channels, because what we have here is 4 plus 4, 8 quad receivers, and we already have 32 channels. But sometimes this may not be enough. So we can have an active distribution system that give us more opportunity and more channels using 2 antennas only. This is an example. So I have a main distributor that's feeding other distributors. So here from a pair of antenna, I'm already feeding, having 64 channels of RF under a single pair of antennas. Would I do more than this? Probably not. If I need to go over 64 channels, in that case, I may think that the installation is very complicated, and I may see the need for different couples of antennas, mostly because they may not cover the same area. But in case the need be, we can have even more complicated distribution systems. Last but not least, I can add another distributor, so up to 5, so another 16 channels to the 64, reaching up to 80 channels with a single pair of antennas. Plus, I can use the RF cascade that is available in certain models. RF cascade is okay as long as you use it as it's in the picture. That means only one level. Why we do not recommend multiple cascade? Because with modern digital devices, we have to filter the cascade output. The cascade output is not just a copy of what we get in, it's a filtered copy of it. So only let's say for X in digital, if this is an A receiver, we only have 470 to 636 at the output. Now, adding one filter is fine, but if we add multiple filters, then our tuning range at the receiver will be shrinked. So we lose the extremes. So for perfect linearity, we recommend to use only one level of cascade. But of course, can be combined with antenna distribution. And if we take this example that was at the maximum, we could have 80 channels. Actually, we can, using the cascade option, reach up to 160 channels. So I think that it's not an everyday job, even for the more clever RF engineers. And most likely, if you have so many transmitters and so many channels on air, and they are operating somehow at the same time, it's most likely that you need to cover different areas, so you may need more than 2 antennas anyway. Checklist for antenna distribution: keep gain and loss maximum to plus minus 5 dB. use as few antennas as practical. So if you need to cover multiple areas, then that's another story. But if possible, use only 2 antennas. Specify quality wireless systems for receiver RF performances. That's to prevent intermodulation to happen inside your rack, creating a little bit unpredictable behavior. And calculate the RF gain structure of your antenna system. This is the last suggestion in our checklist, but the most important. So whenever you have your setup, get a quick calculation. Forward gain of the antenna minus the cable loss minus the split. If a number is between plus and minus 3, then you're fine. If a number is below minus 3, then you may consider to add electric gain stage to your setup. And then multi-room antennas. And so how we can distribute antennas for a multi-room setup. If I need to cover 2 rooms, I may decide to simply passively combine my antennas. Now, for who's paying more attention, there is a price. If you identify in the chat the mistake in this slide, I just noticed it. There is a mistake in this slide. So who notices it wins a little prize kindly offered by me. We can have multiple antenna, multi-room, and we can combine even passively up to 3 pairs of antennas. Very important here, if we use multiple antennas to cover different areas, we should try to minimize the interaction between the antennas. Otherwise, they will have a very strange behavior because they will start interacting with each other and behaving like an antenna array, giving an unpredictable polar pattern as a result. So be very, very careful. If you need to cover different rooms, make sure that the leakage between the different rooms is minimized as much as you can. Another option is to use the quadversity feature in Axin Digital, but this will be a specific topic for an Axin Digital training. That is part of your future, I hope, and will be planned probably somewhere in September. Maybe later, maybe earlier. We'll announce it. Here we have a few drawings, few diagrams taken from different installations, and with active antennas, you may not need to compensate the cable loss because you have already antenna gain stage inside the antennas, but you may need to add additional power like the UA bias that you can see here, that is the DC power supply for your RF lines. And then we can have up to 4 antennas, but 4 antennas for 4 different areas require some special care, or we may, if this is a golf pitch, Lincoln Park, you may have even more complicated antenna systems that in case you're not comfortable with, I highly recommend you to discuss with me or any other technical guy from Shure. We can help you. We had some experiences. I personally made a lot of mistakes, so I can tell you exactly what not to do, at least with a certain level of safety. When you need to combine multiple antennas, in that case, we recommend, if possible, to use an active combiner. The active combiner gives you a few benefits. Passive combiner, as much as splitting, gives you a 3 dB loss. Now, as in this case, you have very long cables pushed with amplifiers. What you really don't want is to lose more signal because of combining state. So an active combiner will be a 1-to-1, like 1 input, 1 output, no change. And it's heavily shielded. It's protecting somehow your signal, so active combiners can be extremely helpful. The limitation is that you need 2. One for antennas A, and one for antennas B. The same combiners that you may use for your in-ear monitors. As per the microphones, when you have multiple in-ear monitors, you really want to use a combiner. Here the limitation is definitely not the sky as it is in the microphone side. So you can combine multiple receivers or multiple receiving antenna or multiple transmitters in case of in-ear monitor into one single feed that can go to a receiver or to an antenna in case of in-ear monitor. The loss of gain is close to unity, meaning whatever you put in goes out. If you are using diversity, you need two, and you may need to add DC bias for active devices if you are using combiners for antenna setup. One thing that I want to discuss with you just before the end, that was probably part of the in-ear monitors topic, but it's worth saying it because it's a mistake I made, honestly, in the past. You may see that the back panel you have multiple input for the signal, and in the front panel you have 3 connectors, actually 4. Maybe they are a little more clear in this slide. So you have main output on the left, then you have A input, B input, and A plus B output. Now, the combiner, the PA421 and PA821, are technically 2 devices in one. So you have with 8 input that gets combined to the output in the front on the left of the device, and then you have all this expansion area. And if you are familiar with PA821 and you try to cascade some of maybe 2 of them, you know that you need to pull a cable from the front panel towards the A input in the front panel, and then you will get the second output from the second combiner going into the B input, and then you have A plus B output. This circuit is completely separated and shielded from the rest of the combiner. So this is a passive Y splitter or combiner, depending how you need it. And this can be used for several applications, but it's completely separated. So you can use it to cascade 2 PIA to 1, but no more than that. Don't use it don't go to the third level. The maximum in your monitors that you can combine is 16, and the maximum that I would recommend is always 16. Definitely do not go over 16. But if you have, let's say, 24 channels to broadcast of in-ear monitors, my recommendation is to keep the most important 8 channels on a single antenna and the other 16 channels on another antenna. Why I'm saying so? Because you want to avoid a combiner, an additional stage that is passive, that means the cascade between 2 PA to 1, because you will lose 50% of your power. So if you are shooting 100 milliwatts out of A plus B, you only have 50 milliwatts left. So this was a thing that I forgot saying when we discussed about in-ear monitors, and I think it's important. Other than that, the combiner is a unity gain, so whatever you put in goes out in the main output, but then you have this additional section that you may decide to use or not. We also have a smaller combiner, and we can describe different scenarios, of course, when you have multiple antenna, you have 2 antenna combiners, so to cover 4 areas, and then antenna distribution. So you may see multiple options on this side. Now, for my presentation today, I'm done. I hope I covered all the topics you were interested in. If you have any question, please let us know, but I don't see any question. So I wish you good luck. Yes, Marwan.
Sorry, there is some questions I believe in the chat, event chat. So the antenna were not at 90 degrees or each other. From Shelton, from
Sorry,
Pavan.
the antennas were not 90 degrees at or each other. Hi Shelton, how are you doing in London, first of all? Sorry, where the antennas were not 90 degrees in the drawing, maybe. Generally, ideally, they should be 90 degrees open. So, but if there was some, no, I got it. You are answering. Now I got it. You were answering to what is the mistake. Oh no, that's not the mistake. I will quickly show you the major mistake that there is in this slide, and you may recognize it or not, but it's not that the antennas are not 90 degrees. If this is what you were referring to. So no one yet won a prize. That is nothing, most likely. But if anyone can catch the mistake in this slide, the prize is still on. In the meanwhile, if we don't have, I keep the slide on so you have more time to look at the mistake. Sorry, someone is writing to me and I think you can see. So other than that,